Okay, so the next topic we can discuss in terms of probability are measures of centrality. And so you have, of course, these full definitions on the handout, so I encourage you to print that out to follow along. But we're going to be talking about two different values that tell us some information about our probability density function. So the first one is the mean, and the mean is the long run average. So again, if you think back to that example about the heights of women, if you were to take the average of all of the measures of your sample, that would be mu. So this is a Greek letter mu, and the way that we calculate the mean using the probability density function is to take the area under the entire curve from negative infinity to infinity of x times f of x dx, because we want to sum up all of our values and divide by the number of values that we're taking. Another useful measure of centrality might be the median. And the median is the x value m, such that the area under the curve from m to infinity is exactly 1/2. This is the middle term. Now, in some probability distributions, the mean and the median are equal, and we'll talk about that in what's called the normal distribution. But that's not always the case. Say you have some probability distribution like so, and it may be the fact that the long run average occurs here, and maybe the median occurs here where the area under the curve is 1/2. So you're not guaranteed that the mean and the median are the same unless you know that you're working with a normal distribution. So what we're going to do is we're going to practice finding both this mean and this median. And so let's go ahead and do that with the problem that is on your handout. So the first example asks us to calculate the mean for a particular probability density function. And so this is the probability density function. So we've got something occurring here with an interesting shape when x is between 0 and 10, and then nothing occurring when x is less than 0 or x is greater than 10. And so this problem is asking us to compute the mean. So using the definition for mu, this is going to be the integral from negative infinity to infinity of x f of x dx. But again, our function's defined in pieces, which means our integral needs to be defined in pieces. So from negative infinity to 0, we've got nothing going on. But when x is between 0 and 10, we've got something kind of interesting going on. But nothing's going on again when x is greater than 10. So from 10 to infinity, nothing's happening. So this calculation, I forgot a key thing. I want to do x times each of these for the mean. It doesn't make anything more interesting happen here. These first two are going to give us no area at all. So we've boiled down to just calculating this middle integral. Now, if you want to see this guy, he does make a more interesting bell curve shape. If you put this integral into Wolfram alpha, you can take a look at it and see. You can verify kind of quickly too that the area under that curve is 1 and that it's always greater than 0, but we're just taking it as a fact that this is a probability density function. So let's take a look at this guy with the x in it so that we can actually compute the mean. So I'm going to take pi over 20 out as a constant and look at the interval from 0 to 10 of x sine pi x over 10. Again, this is a good candidate for integration by parts. We've got an algebraic term and a trigonometric term. So using my little Layate process, I'll pick my u here to be x for integration by parts, and my d will then be dx. So I'll pick my dv to be sine of pi x over 10 dx. And using a little u sub, I can get that the antiderivative of that will be negative 10 over pi cosine pi x over 10. So I just did a little u sub that I didn't show there. in that step. So now we're ready to take these pieces and actually compute this integral. So let's go ahead and do that. So we have our constant pi over 20 still kind of hanging out over here. And it's going to look like I'm going to have negative 10x over pi u and v cosine of pi x over 10 evaluated from 0 to 10. And then the second part, my integral minus my integral of v du. So notice again that I have a negative here. So even though there's a negative in integration by parts, that's going to turn out to be positive. And then I'm going to also take out this 10 over pi, and I'll have the integral from 0 to 10 of v du cosine pi x dx. All right. So I want to notice something about my constants here. Both of these guys have a 10 over pi, so I'm going to go ahead and pull that out, which will leave me negative x cosine pi x over 10. And then I just have to do a little u sub on my second integral. So I'm going to end up with 10 over pi sine of pi x over 10 when I take that antiderivative, and this whole portion here evaluated from 0 to 10. Okay, some nice things are happening over here in my constant. I notice that this works out to just be 1/2, and then I'm going to have to plug in 10 and 0. I'm going to let you guys do that for fun, and we'll see what happens when you do that. We end up with, when all this is said and done in here, a 10. So you plug in 10, you plug in 0. And remember, multiples of even multiples of pi are going to give you, 1 here and 0 here, and odd multiples of pi will be negative 1 and 0 there. So that's not too difficult to evaluate, which means that 5 would be the x value for the mean. Now what's interesting about this is when you go to Wolfram alpha and graph the original integral, just the integral from 0 to 10 of the probability density function, you'll see a nice bell curve come up, and it shouldn't be too surprising that the mean there is 5. And so that's kind of interesting to look at if you want to look at it graphically.